Definition of platinum ore deposits. Platinum ore deposits are naturally occurring concentrations of platinum group elements that can be economically extracted for use. These deposits are notable for their rarity and the complexity of their formation, often occurring in specific geological environments that favor the concentration of platinum and its associated metals. Types of platinum ore deposits. Layered intrusions. One of the most significant sources of platinum, layered intrusions are large, igneous rock formations created by the slow cooling of magma within the Earth's crust. The Bushveld Complex in South Africa is the most prominent example, containing vast reserves of platinum, palladium, and other platinum group elements. These intrusions form when dense, metal-rich layers settle at the bottom of a magma chamber, creating stratified layers of minerals. Magmatic sulfide deposits. These deposits form from the segregation of sulfide minerals within mafic and ultramafic igneous rocks. As the magma cools, immiscible sulfide droplets capture platinum and other metals, forming concentrated ore bodies. Notable examples include the Norilsk-Talnakh deposits in Russia. Alluvial deposits, also known as placer deposits, these are formed by the weathering and erosion of primary platinum sources, with the heavy platinum particles being transported by water and deposited in riverbeds and alluvial plains. Historically significant deposits include those found in the Ural Mountains of Russia. Hydrothermal deposits. These occur when hot, metal-rich fluids circulate through fractures in the Earth's crust, depositing platinum group elements as they cool and react with surrounding rocks. These deposits can be found in association with other valuable minerals such as gold and copper. Geology and formation. Platinum ore deposits are typically associated with ultramafic and mafic igneous rocks, which are rich in magnesium and iron but low in silica. The formation of these deposits involves complex geological processes including partial melting of the mantle, magma differentiation, and the segregation of immiscible sulfide liquids. The precise conditions that lead to the formation of economically viable platinum deposits are still a subject of scientific research, with various theories suggesting roles for factors like magma composition, pressure, temperature, and the presence of other chemical elements. Economic and industrial importance. Platinum is highly valued for its physical and chemical properties, including its resistance to corrosion, high melting point, and catalytic abilities. It is extensively used in various industries such as automotive, for catalytic converters, electronics, jewelry, and chemical processing. The rarity of platinum and the difficulty in extracting it from ore deposits contribute to its high economic value. Mining and extraction. Mining platinum ore deposits requires significant investment and advanced technology due to the depth at which these deposits are often found and the intricate processes needed to separate platinum from other minerals. Common mining methods include underground mining for deep-seated deposits and open-pit mining for shallower ore bodies. The extraction process typically involves crushing the ore, concentrating the platinum-bearing minerals, and then refining these concentrates through smelting and chemical processes to produce pure platinum. Environmental and sustainability considerations. The extraction of platinum, like other mining activities, has environmental impacts including habitat destruction, water pollution, and carbon emissions. Advances in mining technology and environmental regulations aim to reduce these impacts. Additionally, the recycling of platinum from used catalytic converters and other products is an increasingly important source of supply, helping to alleviate some of the demand pressures on natural ore deposits. In conclusion, platinum ore deposits are crucial for the supply of this valuable metal, with their formation and extraction involving complex geological and industrial processes. The unique properties of platinum ensure its continued importance across various high-tech and industrial applications, even as efforts to mitigate the environmental impacts of its extraction are ongoing. Formation of platinum ore deposits. The formation of platinum ore deposits is a complex process involving a variety of geological mechanisms and conditions that enable the concentration of platinum group elements in the Earth's crust. These elements, which include platinum, palladium, rhodium, ruthenium, iridium, and osmium, are typically found in trace amounts in the Earth's mantle. However, certain geological processes can lead to the formation of economically viable concentrations. Geological processes and settings. Magmatic differentiation. This is the primary process responsible for the formation of platinum ore deposits. It occurs in large igneous provinces where magmas, originating from the mantle, ascend into the crust. As the magma cools and crystallizes, heavy minerals containing platinum group elements may settle at the bottom of the magma chamber due to their higher density. This creates layered intrusions with distinct layers of PGE-rich minerals. The Bushveld Complex in South Africa, the Stillwater Complex in the United States, and the Great Dyke in Zimbabwe are prime examples of such formations. Partial melting and magma mixing. Partial melting of the mantle produces magma that is enriched in metals. When this magma interacts with existing crustal rocks, it can lead to the formation of hybrid magmas with varying platinum group elements concentrations. The process of magma mixing, where different batches of magma with distinct compositions interact, can further enhance the concentration of PGEs in certain parts of the magma body. Sulfide saturation and immiscibility. Sulfide saturation in a magma is a critical factor for platinum group elements concentration. When a magma becomes saturated with sulfur, sulfide minerals begin to form. Platinum group elements have a strong affinity for sulfides and are preferentially partitioned into these minerals. As a result, immiscible sulfide droplets can form within the magma, concentrating platinum group elements. These droplets eventually settle and accumulate, creating PGE-rich layers. This process is evident in the Norilsk-Talnakh deposits in Russia. Hydrothermal processes. In some cases, hot, metal-rich fluids can migrate through fractures and faults in the Earth's crust, precipitating platinum group elements as they cool and react with surrounding rocks. These hydrothermal deposits often occur in association with magmatic systems but can also be found in areas of intense tectonic activity. The hydrothermal alteration can lead to the enrichment of platinum group elements in certain zones, contributing to economically viable deposits. Types of platinum ore deposits. Layered mafic ultramafic intrusions. These are the most significant sources of platinum group elements. They form when large volumes of mafic to ultramafic magma intrude into the crust and slowly cool and crystallize. The Bushveld Complex is the largest and most famous example, with its Merensky Reef and UG2 Reef containing vast quantities of platinum and other platinum group elements. Magmatic and ICU PGE sulfide deposits. These deposits are typically associated with rift zones and large igneous provinces. They form from mafic to ultramafic magmas that become saturated with sulfides. As the sulfide droplets segregate, they concentrate platinum group elements along with nickel and copper. The Norilsk-Talnakh region in Russia and the Sudbury Basin in Canada are notable examples. Placer deposits. Over time, weathering and erosion can release platinum group elements from primary magmatic deposits. These metals, being dense, are transported by water and deposited in riverbeds and alluvial plains. Placer deposits are secondary concentrations of platinum group elements and have been historically important sources. The Ural Mountains in Russia and certain regions in Colombia have significant placer platinum deposits. Factors influencing platinum group elements concentration. Magmatic source. The composition of the parent magma is crucial. Magmas derived from deep mantle sources are typically richer in platinum group elements compared to those from crustal sources. Crystallization dynamics. The rate of cooling and the dynamics of crystallization affect how minerals separate and settle. Slow cooling allows for better segregation of platinum group elements, rich minerals. Sulfide saturation levels. Higher sulfur content in the magma promotes the formation of sulfide minerals, which are key to platinum group elements concentration. Geological structures, faults, fractures, and other structural features can control the flow of magmas and hydrothermal fluids, influencing the location and concentration of platinum group elements deposits. Economic and environmental aspects. The extraction of platinum from ore deposits involves mining, crushing, and refining processes. Given the depth and complexity of these deposits, mining operations can be extensive and technologically demanding. Environmental concerns include habitat destruction, pollution from mining operations, and the carbon footprint associated with extraction and refining. Advances in mining technology, stricter environmental regulations, and recycling efforts are essential to address these issues. Recycling of platinum from industrial uses, particularly from catalytic converters in automobiles, has become increasingly important. This not only reduces the demand for newly mined platinum but also mitigates some of the environmental impacts associated with platinum extraction. Conclusion: the formation of platinum ore deposits is a result of intricate geological processes that concentrate these rare elements into economically viable quantities. Understanding these processes is essential for efficient exploration and extraction. As global demand for platinum continues to rise, ongoing research into the genesis and distribution of platinum deposits, along with advancements in mining and recycling technologies, will play a crucial role in meeting future needs sustainably. Properties of platinum ore deposits. Platinum ore deposits are characterized by a range of physical, chemical, and geological properties that make them unique and economically significant. Understanding these properties is essential for effective exploration, mining, and processing of platinum and other platinum group elements. Here's an in-depth look at the various properties of platinum ore deposits. Physical properties. Density and specific gravity. Platinum is a dense metal with a specific gravity of around 21.45 g/cm superscript 3. This high density is shared by other PGEs, which contributes to the ability of these metals to form distinct, heavy mineral layers in magmatic deposits and to be concentrated in alluvial deposits. Hardness. Platinum has a Mohs hardness of 4 to 4.5, which is relatively moderate. This property affects how platinum-bearing rocks are processed, including their crushing and grinding in preparation for further concentration and refining. Color and luster. Platinum typically appears silvery white with a metallic luster. This characteristic can help in the visual identification of platinum in ore samples, although it is often found in combination with other minerals. Chemical properties. Resistance to corrosion. One of platinum's most remarkable chemical properties is its resistance to corrosion and tarnish. This makes it valuable for applications in harsh chemical environments and is a reason why it remains stable over geological timescales. Chemical stability. Platinum does not react easily with most chemicals. It is resistant to oxidation and acid attack, with the exception of aqua regia, a mixture of nitric acid and hydrochloric acid, which can dissolve it. Catalytic properties. Platinum is an excellent catalyst, facilitating various chemical reactions without undergoing changes itself. This property underlies its extensive use in catalytic converters, industrial processes, and laboratory equipment. Geological properties. Association with mafic and ultramafic rocks. Platinum deposits are predominantly found in mafic and ultramafic igneous rocks, which are rich in iron and magnesium but low in silica. These rock types are typical in the Earth's mantle and are brought to the surface through tectonic processes. Layered intrusions. Platinum ores are often located within large, layered igneous intrusions, such as the Bushveld Complex in South Africa. These intrusions form when magma cools and crystallizes in a layered structure, with dense, metal-rich minerals settling at the bottom. Presence of sulfide minerals. In many platinum deposits, platinum group elements are found in association with sulfide minerals such as pyrrhotite, pentlandite, and chalcopyrite. These sulfides can capture and concentrate platinum during the cooling of magma. Mineralogical properties. Platinum group minerals. Platinum is often found in nature as native platinum or in combination with other platinum group elements in minerals such as sperrylite, cooperite, and bragite. These minerals can vary significantly in their appearance and properties. Textures and structures. The textures of platinum ore can range from disseminated particles within host rock to massive sulfide layers. The specific texture and structure affect how the ore is processed and beneficiated. Economic properties. Grade and concentration. The economic viability of a platinum deposit depends heavily on the grade, which is the concentration of platinum and other valuable platinum group elements within the ore. High-grade deposits are more profitable to mine. Byproducts. Platinum ore deposits often contain other valuable metals such as palladium, rhodium, nickel, and copper. The presence of these byproducts can enhance the economic value of a platinum mining operation. Extraction and processing costs. The depth at which platinum deposits are found, the complexity of the ore body, and the presence of other metals influence the cost of extraction and processing. Technological advancements aim to reduce these costs and improve efficiency. Environmental properties. Environmental impact. Mining and processing platinum can have significant environmental impacts, including habitat destruction, water pollution, and carbon emissions. Managing these impacts is crucial for sustainable operations. Recycling and sustainability. Given the environmental and economic costs of mining, recycling platinum from used products, such as catalytic converters, has become increasingly important. This reduces the demand for newly mined platinum and mitigates some environmental impacts. Conclusion. The properties of platinum ore deposits encompass a wide range of physical, chemical, geological, mineralogical, economic, and environmental aspects. These properties not only define the nature and distribution of platinum in the Earth's crust but also determine the methods used for exploration, extraction, and processing. Understanding these properties is crucial for the efficient and sustainable utilization of platinum resources, which play a vital role in various high-tech and industrial applications. As demand for platinum continues to grow, advancements in mining technology, recycling, and environmental management will be essential to meet this demand responsibly.